Gonna wait until I actually get to be live. Looks like we're kicking off. Perfect. All right, and I'm gonna let a couple people know. That'll edit out the start of the stream. It's hard to multitask, so I'm going to try to avoid it, but the short version is I'm just letting a couple people know, and a couple people that I'm working with is on no. Stream. Twitch.tv. This should be me. There we go. Just watching the stream content. Waiting for myself to be online, which should be any second now. There's a little bit of a stream delay, I think. Aha. There we go. I have two Twitch dashboards. One of them is associated with an email account that I kind of don't use, and the other is associated with just an old account. So we should be good now. Perfect. All right. So the thing that we want to set up today is a model that will, given two skeletons and two bone indices or two bone names, tell us whether or not they are the same bone. We don't have a whole lot of training data for this. We have a data set from Mixamo, or from somebody that pulled Mixamo, which contains 25 skeletons. And fortunately, the skeletons seem like they have the same names. So I have here Abe, which has hips, spine, spine 1, and then AJ, who has also hips, spine 1, spine 1. Oh, if this does not, then hips, spine, spine 1, but in a slightly different order. Fortunately, these should kind of roughly match with each other, but still, 25 skeletons is not a whole lot of data. Even if we decide to go the route where we pairwise compare hips to hips, hips to left foot, and so forth and so on. But given the limited data that we've got, the thing that made the most sense to me was a decision tree, just because it works well for tabular data, it works well for small amounts of data, and if we decide that we really have to, we could do something like a decision forest or something to that effect. So I discovered while making this project that I had actually already written out a decision tree. So I'm going to start by just kind of going through what the decision tree does, what it how the code is sort of generally structured, and then we'll go through the process of doing our data munging and the training itself. So to help illustrate, I'm going to pull out MS Paint, and for anybody that just happens to be watching, if you want to decide something like, am I going to play tennis today? You might have a couple of factors like the weather, I'd say hot or cold, the humidity, this is wet or dry, and then some other factor like, I don't know, sunlight, sunny or cloudy. I think that's the traditional example that everybody gives. And then you have a series of examples, and you don't know exactly what... ML is always a case where you don't know exactly how to get to a given outcome, but you have lots of examples from which to train your output. So let's say we happen to have, I don't know, let me use my pen instead of this, and brush. Make this a little bigger. Size, there we go. Hopefully this is more visible. We've got this dynamic table of the, I don't know, played tennis, yes. When it was weather, humidity, and then sunlight. And I'm going to say 1 or 0. I'm putting this backwards just out of spite. I did play tennis when it was cold outside, and it was dry, and it was sunny. I decided to not play tennis when it was hot and wet and cloudy. That sounds like a recipe for disaster. I did play tennis and it was hot and dry and sunny. So this is just an example. So we'll have a bunch of these, and ultimately what we want to say is, given the factors wet, hot, and sunny, am I going to play tennis or not? Very similarly, we've got a bunch of bones whose data we can actually pull, like our rotation, our transform. We could augment this with data, which is called feature engineering, and say, will I eventually do these two bones, given these features, match up with each other? To do that, our decision tree basically will go through all the different things on which we can make a decision. Like, we start by iterating over the different items that we can decide on. This is the first time I'm seeing this code in 5 months, because I made it and then forgot, and now I'm coming back to it. But what we're going to do is we're going to, given a bunch of examples, go over all of them for each of the possible features that we could have. And then if there's a really flagrant separation, like if there's one thing that always makes an obvious choice, we're going to use that as our sort of fork in the road. And then if we are, in the one case, we're going to jump to the left subtree, and the other we'll jump to the right. And what that means basically is we can recursively make decisions about how we want to split up our data, with the hopes of eventually coming to a decision. So let me go over exactly, that's a high-level overview of how the source is going to work, but the low-level view, let me see, do I want to get into that now, or do we want to get into that in a little bit? I guess one question that usually comes up is, how exactly do we make the decision? And there's something called Gini impurity, which is a representation, there are 3 different ways, but one of the standard approaches with, I think, the ID3 process is we want to find the maximal purity after the split. And to do that, we calculate what's called the Gini impurity. And that's basically just a measure of how much information gain do we get if we split on this feature. Like if I, in the previous case, said, I think I'd like to split on hot. So when it is hot, I know that I never play tennis. When it's not hot, then yeah, I always play tennis. So that gives us a very high, very clean information split. So that's where I want to make my decision. And we just repeat that every time, passing the other factors or the other examples that happen to match this into the children as we build this out. So that's how this works. I am not going to use it yet, but you'll notice that I've wrapped it into a decision tree file that happens to support exporting itself or saving itself as JSON. So we can train this up via just the train example, and we pass in this array of samples along with the array of labels, which in this case is just going to be a Boolean, I believe. And then we'll save this out to a file. I'll get into more of the details, and I can get into the actual code itself if people decide they want to see that. But I'm going to be doing a little bit of data munging, because that's going to be 99% of this project. And to do that, I have this VRM remapper that I kind of started setting up. And this method, getFeaturesForSkeleton, is what's going to take a skeleton and a bone and spit back this list of properties for a skeleton. So you'll see when we go to make a decision inside of the decision tree, one of the things that predict has is a sample array. And sample just means I can give you an example here. Similar to how we had hot, sunny, cold, whatever in the other one, we might have this could be number of siblings, which in this case, so if this is a root bone, maybe one sibling. What is the transform? It could be 0, 0, 0. So I'm separating out X, Y, and Z into separate features. I might have the distance to the nearest item as a feature. So it could be 0.1 centimeters or whatever away from the next item. But this is called feature engineering. It's the idea of taking something and converting it into basically a table of features. So we're going to do that now for a skeleton. And I'm going to probably flounder a little bit because I only have, flounder only a little bit because, it's been a while since I've looked at skeletons. But yeah, make features for skeleton right here is going to take our skeleton. It's going to spit out a dictionary. And I'm kind of tempted to, if we're doing the entire skeleton at once, then there's it'll be a little bit harder in some ways and a little bit easier in others. It'll be a little harder because when we actually have to do this at runtime or inference time, we might have to provide the entire skeleton, which isn't a bad thing, but it's a little more, it might be easier to encapsulate if we just take a skeleton and then a bone, and then we'll just, from where our bone is, have to figure out all the rest of the properties. So maybe I'll do that. Maybe I won't. One of the things that will be much easier with taking the entire skeleton and computing all of it at once is the depth of the bone. And that's a feature that I'm fairly certain will be useful information. The root bone is probably going to have depth 0. Probably. Not absolutely certain, but it seems overwhelmingly likely to me. Something like a pinky bone or something like that is probably not going to have any child nodes. It's possible, but doesn't seem particularly likely to me. So that's one of those things that we can get from just the bone and don't need the whole skeleton. But yeah, either way. So less dilly-dallying. I'm going to start with make features for skeleton, and yeah, I think I'm going to start here. So what are some of the features that we want for a node? I think position X, Y, Z would be useful. Start rotation, though this might actually not help us depending on whether, if we assume all of them are in T-pose at the start, which is maybe not an unfair assumption, then this could cause problems if they're way outside of line. But for now, I'm just going to include them as features, and then we can turn them off if we decide to. iFire says, holding a whip is an example of a hand bone having a child bone. That's, yeah, perfectly right. If you have a model which does, in fact, have a whip where they are constantly bound to it and they don't use a bone attachment point, then they will, yeah. Especially if it's hardwired into the skeleton, then yeah, it's going to have a child node. But in any case, I'm just going to take all the factors for the transform, scale, all the real factors for it. So rotation does have extra factors like X, Y, Z, and then delete for the quaternion. What's this? Use orthogonal basis Euler and quaternion. Yeah. I agree. So iFire's point is that if you use another encoding like Euler angles instead of using the orthonormal basis, then you have some crazy stuff that can happen. I think it might make sense to use normalized quaternions, but it would just be easier to split rotation into the X vector, Y vector, and Z vector. And this will give us actually more separate things, which it might hurt us, honestly. It might help us. So I'm not sure whether I want to do that. So the advantage to using the quaternion XYZW is that the representation is denser in the sense that when we're doing a comparison, the advantage in Euler is the model right now has many poles and quaternion has 2 representation. Yeah. So the advantage to Euler, just when it comes to how I think it's going to act with the decision tree, is the metric that we're using for splitting based on impurity is going to, let me turn that off, is we're doing a naive comparison for the sample, basically. Like the place where we select our sample, I believe, is the mean of the values. And I need to check that because, again, it's been 5 months since I looked at this code. I think probability of gene impurity. What I want to find is where we're actually doing this split. Here we go. Lowest impurity index. And to do that, weighted impurity index, lowest impurity, left candidate labels. So our division is naive. We're just using 0.5, which I think, are we just going through the candidate columns? Probability by category. Oh, so we're using categorical labels. Oops. I can go back and I might change this. Yeah. It might be distracting to explain exactly what I mean by probability by category. Yeah, I will explain this because I think it's going to help. So this is a simple approach to just counting things out. Probability by category, let me add documentation. It takes an array of labels and spits out the probability of a given category. Probability of a given I just realized how loud my keyboard is when I actually type. I just swapped it out yesterday because my other keyboard's period died. So hard to type without that, despite how I speak. Via counting. All we do is count the total number of items and then count the number inside the category versus the total count. So if you have 1 red ball, 9 green balls, the probability of red ball is basically 0.1 or 10%. And that's what this is doing by category. The labels, however, are kind of yes, no. So what's the way to say this? Count by category. If we have labels of just an array of true, false, for example, true, false, then it'll tell us what percentage are true and what percentage are false. That's what this will accomplish. But so that's how this is used. But I don't think that our actual decision is made by probability by category label. So this is the current impurity, and then our split just goes over the columns, I think. So range in the samples. The candidate column is what we're looking at. So yes, we only have 1, 0, which means that we're assuming binary features, and that's not necessarily a great thing. So I might have to come back later and change this to something like the mean or the median or something to that effect. But I'm going to make a note here that says do change this to use the median of the values. Using the median or mean of the values can be problematic, especially if there's homogeneity inside of a column. We shouldn't get that, especially because well, no, actually that can happen all the time. If we make a split and suddenly all the columns are uniform, then that's a bad feature on which to decide. But all this is to say, when we are doing the VRM remap, splitting out the rotation in this way, it's more useful if we can have a bunch of values which are between 0 and 1, and that's kind of why I'm leaning towards quaternion representation, because we can renormalize the x, the y, the z, and then the w from the -1, 1 range into a 0, 1 range. I'm getting way ahead of myself though. We still have to actually produce these features. So I've got the parent, go and get parent. I think I wanted to use the name at some point, but all the names are going to be the same. See another comment? Quaternion has two representations for the same rotation. That is true. And I don't think that's the sort of thing that we can get away from by renormalizing either. But it's a problem that I'm going to... Actually, in that context, because these rotations, like if we use the xvec, yvec, and zvec split out, I think those have to be normalized. They'll still be between like -1 and 1 on all of the angles, so that might even be the better approach now that I'm thinking about it. Yeah, so that's probably what I'll do. It'll mean we have a lot of columns with zeros, but honestly, I think that's kind of okay. All right, so position XYZ, rotation XYZ. We've got scale. I also would really like depth, and I would really like number of children. So let's start with our feature now, which is just going to be this empty list, and we will begin by saying our pose, which I believe is a transform, and I'm going to get skeleton dot get. Sorry, I need the get pose, get bone. I'm not sure if I want to use global pose or just the pose. I'm tempted to. I might get the rest pose, honestly. Oh, no, DX. That seems like the right thing to do. Yeah, if I do get global pose, then so ifire again says get global pose. If I get the global pose, then we're gonna have scaling stuff that we need to worry about, and this kinda sorta might renormalize it. I'm not decided if I want to use the global pose yet or not, but I don't know. Actually, that's worth making a note about. So get global pose? Question mark. Get global rest pose. Oh. Reset has been changed between 3 and 4. So right now I'm using 3.5 release candidate 1, or release candidate 6. I think this should be like, most of this was built with 3.5, and if we do the 4.0 alpha, then a lot of it's going to need to get updated. But fortunately, because we're consistent in the way that we save and load the JSON, we won't have to update the model. We just have to update the way that it's being trained. So for now, I'm going to stick with the pose. And then for my feature, I'm going to say this is going to be the pose dot, I think x, oh, sorry, pose origin dot x, pose dot origin y, pose dot origin dot z. And just for formatting's sake, I'm going to split this out. Then I will have the pose dot basis dot x dot x is going to be a vector of 3 components, I think. This could be basis dot x is a vec3, I think. Basis. I think basis does have, yeah, it's a vector of 3 elements. So it would be x dot x, x dot y, x dot z. All right. Basis x dot x, pose dot basis dot x dot y, pose dot basis dot x dot z. And if if you hear me switching between the z and z all the time, it's because half of my coworkers were from Great Britain. That you only need 6 floats. Yeah. Indeed. So there are 6 degrees of freedom with an arbitrary... sorry, iFire's point was there's a theorem that says you only need 6 floats, and that's completely true. If you have 6 degrees of freedom, you need 6 numbers to represent that. A lot of what we do with feature engineering is actually making some of the data redundant. You take it, you augment the data, and then you spit it out into a different format, because although you can flatly represent things as just 6 floating point numbers, sometimes it helps a model learn if you have a layer of abstraction on top of that data, because you can take your domain knowledge and sort of zhuzh up to make things more obvious to the machine where patterns might exist. Like, think of it as like if you we're trying to categorize groceries, and you happen to augment this with the feature that is the distance from the center of the store as viewed from the top. The machine might actually discover that. So if I happen to have my grocery store, which is like this, and then I augment it with a feature that says D. So pencil, this is D. The distance from the center. It turns out that around the outside of the grocery store, there are like the baked goods, and then meats, and then frozen vegetables, and then breads. And then everything inside is processed goods. And it turns out it learns that, oh, once D is above a certain value, then it happens to be healthier. So we could have the x coordinate, the y coordinate, and the distance, or we could just have the x coordinate and the y coordinate and let it figure out how to augment that together to, like, you know, put together a distance metric. In this case, although it's redundant to have the extra information about the pose basis for x, y, and z, like I only need 6 of these numbers, and then the cross product of the x and the y will give us z. But if I have more than that, it can make it useful for a decision tree or for some kind of model that wants to figure out the extra info. So going to duplicate this one more time and give it the extra admittedly duplicative information. And then finally pose dot, excuse me, I think scale, no, I'm not going to do scaled. Pose dot, I don't remember if basis actually has the scale. It does. But I think that scale might be baked into XYZ. So I'm going to leave it off for now, and then just make a comment like scale. Other features that I want are the depth, and looks like I have bone depths already. So if bone depths dot has bone IDX. Sorry, I don't remember if the bone parent returns the parent index or the actual parent. I think get bone parent help skeleton. Get bone parent returns the parent index. Bone index, which is the parent of the bone of bone IDX. If it's -1, no parent. Okay, great. So this is going to be an integer, and if parent is -1, then bone depths of bone IDX is equal to 0. Otherwise, there is the possibility that we encounter this before the parent. Hang on, I see some comments coming in. Basis.getScale. Orthonormalize removed scales. Count the number of parents for rank. I think that a bone can only have a single parent, though. So in that case, I'm gonna. My thinking is I would love to be able to just say like bone depths. Bone IDX is equal to the bone depths of the parent plus 1, which would make sense, but we don't know that we're going to hit it necessarily in the right order. We could, in theory, parent of parent of parent of parents. We could go through more than once and just sort of recursively evaluate this, which I actually kind of want to do. And that would give us the full details for like the depth, and that's not the worst idea in the world. Do I want to do that? Kinda, sorta, but also not really. Mostly because we're putting everything inside of this make features for skeleton function. No, I should stop being lazy and just make it happen. So let's make that happen. Func compute bone depth and child count. So this is going to take skeleton and give back a dictionary with returns a mapping from bone index to, I'm going to call it another object. So I hate to return it in terms of like children, depth, int, and then siblings, int. Mostly I just don't like stringly typed things, but this might be the only way. So at a given point, we can compute we can insert the number of siblings that a child has, and we can count the number of children that we've got, and then depth will give us the information that we need. So I'm going to start this with a bone ID, and if I say bone IDX is -1, then that gives us our base case. Of course, I have to return the result set. I'm going to call this skeleton info because I think that's more descriptive. Skeleton info. Hello, my name is skeleton info. And now, if bone index is -1, then we're basically at the very start. We don't have to, like, we need to initialize the info. Skeleton info. Oh, sorry. You can tell I've been programming in Python for the past like week because I throw away the variable names, or throw away the var before actually initializing stuff. And dictionary is not the type; it's dictionary.new. All right. New is not present. I think this is dictionary like that. Yeah, there we go. And skeleton info is wrong because it should be skeleton info. Hello, my name is skeleton info. Cool. I'm going to start with cursory pass. I think bone IDX, actually, let's make this, I don't know if we can always say that a skeleton has bone 0. We might not actually have that info. So I'm going to say if bone index is -1, then we need to find the first bone. So for bone IDX in skeleton.getBoneCount, I'm pretty sure that we can say that, yeah, -1 is invalid bone, but do we always have a bone 0? We might not. My thinking is like, there's the defensive programming approach where we can't guarantee that we've got bone 0, but we might. All right, I take it back. So I'm going to say bone 0, and then I'm just going to load up an assumption. Assume that our skeleton always has at least one bone. It's possible it won't. Exactly, yeah, the skeleton might not have any bones. Assert skeleton dot get bone count is greater than 0. So at least we'll get an assertion error if that fails. If not, then not gonna sweat it. Assert, and I don't remember if GD script requires parentheses. It does. All right. So we want the depth. So if I'm also going to get the parent here, IDX int is equal to ton.get parent, which get bone parent of our current bone index, bone IDX. If parent IDX is 0, then we're at the root, and we can say that our skeleton info for our I'm debating where I want to add the info. Initialize our skeleton info for bone IDX is equal to children, none yet, depth, 0 so far, siblings, none that we know of. And now, if we do not have a parent, then the depth is still 0. If our depth is greater than 0. Okay, depth is actually not something that we need to worry about now. I take that back. So don't worry about depth for this node. It will be assigned by the parent. The same apply. I'm just going to mark down what we can derive from the current instance and what we can derive from. Wait, hold on. Godot can actually have multiple roots of the skeleton. That's a good call out. I might ignore it for now and come back to it, but I'll make a note. To do handle multiple roots of the skeleton. So when we iterate over the list of all the bones, we might actually not have something that's, or might have something that's unconnected, which would be weird, but it's a case that we should handle. Fill in here. Let parent fill this in. Okay, so we've got two operations that we need to fill in. We need to fill in the children for the current node, and then for each of our children, we need to give their depths and their number of siblings. So again, I have to do the parent IDX. I have to put this back. Skeleton.get parent, and then get bone parent of bone IDX. And then just to handle the base case, if parent IDX is -1, then skeleton info IDX depth equals 0. This is pretty much, yeah, well, I just need to have that there. All right, and now we can actually fill in the information about the siblings and the children for the current node. So, skeleton.get child count, I think, bone child count, bone child count. There is I think by iterating over, there's no like bone.get children. I think we only have the pointer from the children to the parent. I'm gonna double check that. I think get children operates on the node basis, and we're not gonna see like necessarily see the. What's that? I have to make a dictionary for all bones in the parent. Yeah, I'll. There are ways around it. If we don't have direct access to the children, then what I'll do is I will iterate over. I'm going to fake it by basically iterating over all the bones, and then this is wasteful, I know, but it's a hack and it'll work, and it'll probably make things a little simpler. So I don't see. Yeah, I see get bone parent. I don't see get bone children. Yeah, unparent, blah, 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 blah. Yeah, that's fine. Okay. So I'm going to make a note saying why we're doing this madness. Note. There's no way to get the children of a bone via method call. Sorry, function call. So we iterate over and check the nodes which have this as a parent. So child bone IDs. This is going to be an array of integers. For a moment, int pool array. Yeah, I'm going to do int pool array. pooled int array, pool int array. Not that it matters that much. And then for child bone ID in skeleton, get bone count in range 0 to get bone count if skeleton dot get parent bone parent every time parent of child bone ID equal to this bone ID, then bone IDs append child bone ID. Not very pretty. I think I'm also gonna replace bone index with bone ID and parent index with parent ID. It's stylistically from different languages. Some of them use IDX, some of them use ID. It's just a matter of preference. So now we've got a list of all the child bone IDs, and that gives us the information that we want. So skeleton info for the current bone ID, children is equal to the length of the child bone IDs. One piece of the puzzle down, and then for each of the children, we will populate this info, then call it, with our, I will apologize for this stupid hack in a little while. Skeleton info is a dictionary, which we are going to set to null. Yes, really. If skeleton info is null, then skeleton info. So we're just initializing our skeleton if it's unset. I hate this typing. There's no option typing here. So skeleton info is going to be a dictionary. We're kind of, this is a sort of hack. And then if skeleton info dot skeleton info dot has bone ID. If not, if we have no info, like if we haven't initialized yet, then we're going to initialize it with this base info. And after this, we can guarantee that we got the bone ID. All right. So now we've got our children info set. We can set our depth, skeleton info, bone ID. Did I already reset the depth to, yeah, I set the depth to 0. So count it equals 0, else if skeleton info. I'm tempted to, like, I'm sort of bouncing around for where I'm setting these things, either in the level call or in the recursive child call, so that might get a little on the messy side. I'm thinking, I'm going to say depth. Sorry, children. Yeah, sorry, and now we need to actually do the assignment for the child nodes that we care about. So the children we fill in here, the depth. So we need to fill this in for all of our child nodes. So for child ID in child bone IDs, skeleton info, if skeleton info dot has child ID, skeleton info of child ID is equal to a new dictionary with children 0, depth is equal to the skeleton info of our current self, bone ID, depth plus 1, and then comma the siblings, siblings is going to be the length of the child bone IDs. This fills it in for all of them. And then I'm also going to step through, like we could do the recursive call here. Info. If it does not have this, then we fill it in. It's possible we might want to just pre-allocate and then set the data. Now I'm going to just say don't override if it's set. And then we can do the recursive call again here. So compute bone depth and child count. And we're going to do that for skeleton, for the child bone ID, and given our skeleton info. And then finally, we can, so this will set the depth, this will set the children for that. And then we can just return the skeleton info. So this will give us what we need for everything if we start at the root. It's not going to handle the attached, like the detached root, because we're starting at 0 and there might be multiple detached ones. How do we resolve that? One option would be, sorry, I'm looking at the scroll back comments. And their parent. Yeah, so an option for what we're doing next. I think we can just iterate over everything. Sorry. Using parent equals -1. Yeah, that's exactly what I think I'm going to do. So iterate over all the bones in the method that's going to call this. If they don't have a parent, then just perform this root call. So we just find all the roots of the tree and then do exactly this operation. So fortunately, bone depths, this can go away. This compute operation can go away. I think this can go away as well. So for each bone, it's a root node. Compute the properties it needs. Properties it needs. And bone depth info is going to be a dictionary. So I'm pre-allocating this dictionary. This, in theory, should never be a thing, but just in case. I think I'm not going to have this return a dictionary. I'm just going to say, like, mutates the given skeleton info dictionary. And then this has to be a dictionary. And I will move this to and that'll be the output. Then we can get rid of this. It doesn't return a mapping, but it will have sets a mapping from bone index to that. All right, and then yeah, I kind of like this so far. So we pre-allocate our bone depth info. We call for each bone for bone index in skeleton.getBoneCount. I'm going to do range again because it just saying in kind of bothers me, and I don't want to get confused. If skeleton.get parent, bone parent of the bone ID, that is, if this is a root bone, then compute bone depth and child count for this skeleton, which we pass by reference, for the given bone ID, and we pass the bone depth info dictionary to be mutated. Cool. And now we're going to go through again, and we're going to build the mapping from bone, I'm going to say bone ID to a feature array. We could make this a type, but I'm not going to do that. All right. So our feature is an array, excuse me, position feature is this. We have the origin, we have the rotation, position, rotation, scale, I'm not going to touch right now. Then we want depth, which is going to be the bone depth info of the bone ID. And again, I'm going to change this to bone ID. And this is depth. Number of children. Count. I'm just going to call this whole section meta info. Sorry, hierarchy info. Hierarchy info. Bone depth info. Bone ID. Children. And again, these are just integer values. Oh, actually, that's an interesting point. So, I see a point. There are lots of problems when bones are skipped between named bones. When bones are skipped between named bones. So if we have the skeleton bone names. I'm not sure I understand the point. Class names are so fragile. Yeah, I haven't bumped into any super terrible tragedies with class names, but I do. Yeah, the GD script, for as nice as it can be, also has some interesting warts, I'll say. So, I'll make it work, and then we can try and worry about the other pieces. One thing that I wish I could do, but I can't because we need to rely on the bone names, is hang on, root, random hip, spine, chest, upper, chest, neck, head. The one in the bone names. Yeah, so skipping bones between bones. I don't want to say that I don't care. If bones are, whether bones are the same or not is something that we kind of have to, like, it is not well defined. For example, let's say we have let's say we have a leg with 4 bones in it. I'm sorry, just a shin with 4 bones in it. So this is our shin. It happens to be a straight line. This is the knee. Change the size here. This is our knee, and this is the heel. For whatever reason, let's say we have two bones that are in the middle, and I've seen this before. So instead of there being just the one bone from like the knee to the shin, which is what I would hope for, there are 3. There's one that has root here and goes down here, and there's one that has root here and goes down here, and then there's one that exists here and goes down here. So the mapping between these 3 bones and the one like actual bone is something that's kind of fuzzy. I'm tempted very much to ignore these 2 because I think that as long as the names are consistent between these 2 bones, the rotation info that we get from this one will win out, and eventually it'll be okay. Yeah, twist bones are an absolute mess, and I don't want to say I hate them. I mean, they're a pain, but this is one of the things that I'm worried about. But when we actually do iterate through, we're going to get like these bones will say like twist ankle 1, twist ankle 2, or twist chin, whatever. So I'm just going to rely on there not being a match between this bone's name and this bone's name, between the skeletons. All right. So this will cause issues with like depth and stuff mismatching, but that's okay. Like we want the bones which don't have an obvious match to have a mismatch in their depth or their children or something else. So that depth info bone ID, and the reason that we want that mismatch is so that we don't try and correspond the bendy bones or the whatever you call them, the flex bones, to what's actually like a functional bone. Siblings. Something that I realized to do normalize is we need to convert these from integers into either floats, or we need to support floats better. So I think what I'm gonna do is I think I'll normalize the value for these by dividing by the number of bones. That means that, like, at most, the depth of a tree with n nodes is n. So it's just like a linked list with all the things going all the way down. The maximum number of children that a thing can have would be the stump, where it's a single node and then all the children. So all of these are basically guaranteed to be between 0 and the number of bones, and therefore dividing by the bone count is just going to make them floats between 0 and 1. Bone count is equal to skeleton get count. And I think I need to force this as a float. Divide by float bone count. I'm probably throwing too many parentheses at this, but I kind of don't care, because I'd rather have too many than too few. And I've been bitten by that before. Okay. So now this is normalized between 0 and 1. That's the hierarchy info we need. That's a feature. I am content with this. We should probably normalize the pose origin to be 0, 1. Like if we divide by the maximum height of the bounding box for the skeleton, then do we want to do that? Thinking. Just to make sure that it's all inside of like the 0, 1 range, because that gives us nicer features. Parentheses. Yeah, it's definitely a C fascination with parentheses. It's because, like, here's an example. Is the result positive or negative when B is greater than A? Dunno. How about now? I should have picked 4 because then... But you'll see that these are very different, and sometimes it's ambiguous. I know there's the whole PEMDAS, but if the order of operations is ambiguous, then... Yeah. Yes, exactly. So that's why I'm throwing parentheses at this thing, because I don't want to end up in the case where, like, and this has happened to me, like if I don't wrap this in a float, then, or if I don't specify this as a float, then I don't know what GD script is going to do as far as type coercion is concerned. Sometimes it might coerce it to, Hackery says it's not ambiguous, I just don't remember the chart. And if you don't remember it, then... Okay, yeah, I am misstating. It's not ambiguous. When I say ambiguous, I mean, like, it's not that it's ill-defined. It's just that if I'm looking at it and I don't remember the chart, then it's ambiguous to me. Not ambiguous in, like, the grand scheme of things, just ambiguous to me. So, that's why I throw parentheses at everything. My solution to all problems in life is to use more parentheses. Okay, so we have a couple of features. This is probably good enough for now. I need to actually set like result bone ID equal to feature. Actually, I don't even need to do. I can just do it right here. And I think that I can eliminate because it's basically duplicated down here. And that will return result. We compute this for all the bones, and that gives us the features for the skeleton. So now comes the actual hard part. I'm going to make a quick note. Wish I could do stuff with names. Because I really was hoping for a trigram solution. All right. How will we represent the mapping between the target skeleton and the bone? Great question. So eventually, what we're going to do is we're going to be doing a pairwise iteration. That's going to be like 48 times 48 comparisons. And we'll say, are these the same bone? And our model is going to spit out they're the same bone or they're different bones. And this is going to work for any two skeletons, is the nice point. So even if we don't have like so previously iFire and I were talking about like, do we want to be able to retarget skeletons from like a generic, like to a generic target or just to anyone in particular? For the people that are playing the home game, just imagine that we've got a skeleton. If we're trying to find the mapping between something with clavicle bones, 4 bones, and then just three fingers, like the pinky, the middle 3, and then the thumb, shoulder blade, upper arm, lower arm, 3 fingers, and we're mapping this. Let's see, 2, 3, 4 skeletons: right hip, left hip, right upper leg, right lower leg, heel bone, and then same thing for this side. And then we've got another skeleton which has the top of the head, neck, no shoulders, but upper arm, lower arm, 1, 2, 3, 4, and a thumb. Upper arm, lower arm, 1, 2, 3, 4, and a thumb. And then just 2 skeleton segments, no hips, right leg, foot, left leg, foot. If we have a skeleton, if we say, okay, no matter what, how you represent the mapping? Sorry, same question. If we say, okay, this is going to be our skeleton. This is the end-all be-all skeleton. No matter what we do, we're eventually going to map to this. Then what I would do instead of like the thing that we're doing now is I would grab a handful of models and I would say the mapping from this bone is to this one. And then I'd pick another model, another skeleton that was much simpler, and I would give it the mappings between all the bones. And then instead of predicting, are these 2 bones the same, I would say, to what bone on the ultimate skeleton does this correspond? In that case, the input, option 1, the input is basically a bone. Bone. Out is matching bone. Bone. Then option 2, our input is our 2 bones, bone A and bone B. And our out is same or different. So we are using this approach where we give it 2 bones and we say whether they're the same. How will you represent the mapping between the bone and the bone? So the way that we're going to represent the mapping is we will, after we iterate over all pairs of bones, so if there are 48 in here and there are 48 in here, we will end up with a 48 by 48 matrix that says basically, are these bones the same? Are these bones the same? Or it'll be number of bones in skeleton by number of bones in this skeleton wide. And it'll give us a table with like, imagine a heat map or a confusion matrix that will say, this is the most likely correspondence between these bones. We can then find the path between the top left corner and the bottom right-hand corner that maximizes the number of matches without duplications. there's a greedy algorithm that you can use that basically pathfinds using the best possible matches. And using that, we say, okay, this maximizes the total matching between these two skeletons. So that's kind of what we're going for. So now that we've got make features for skeleton and the compute depth and child count, we're going to do this for the pairs of skeletons that we have inside of the VRM remapper. I think, yeah, 3D. So this is just a node, but what I'm going to do is I'm going to add Abe, AJ. I'm going to go basically brute force for all of these skeletons, and the ground truth for two bones matching. How do we summarize? The question is, how do we summate the skeleton by skeleton training? I'm just about to get to that. So the VRM remapper is going to have a bunch of child skeletons. So inside of this, I'll have Abe, AJ, whatever the, like if I open up Blender, I've just been opening up the skeletons and then doing one reset pose and then exporting them as FBX files. And then I got it right here. So Abe, it's going to take a second to load, has all these bones. But the important part is that there are matching bones between Abe and AJ. So it might help a little bit, I think, if I just like actually write this out. So train. For training, we want to build all possible pairs of bones, which means we've got 25 skeletons times the number of different like child bones. And because the names have overlap, I'm eventually going to have like this list of triplets where you've got bone property A, or bone properties A, bone properties B, and then 1 or 0 if they happen to match. And we're going to have a bunch of these. Then we'll take all this, we'll throw it into the decision tree, we'll train it out, we'll see how it does, and then, yeah, maybe it works, maybe it doesn't. Okay, so the thing that we need to do, we have Abe FD FBX, which I already had open. No, don't reopen. I am going to drag this into the root. Going to get rid of this root, including the animation player. I think I actually don't need like these child nodes because they're already like there are already bones inside of the skeleton. So I'm just going to delete this and see. Yeah, we've still got the skeleton. Oh, I did delete the animation though. That's fine. And then scene, save scene as, and I'm going to call this Abe TSCN. Same with AJ. I might make the root. Okay, hang on. Let me try this real quick and see if it... Yeah, this will be fine. And then I'm going to delete all the bones. I think that the bones should be named. Yeah, left hand ring. Oh, this is great. They're actually in a different order. Yes. That is very important. So, and then I'm going to save scene as AJ. Inside of our VRM mapper, I'm going to instance child scene. I'm going to instance AJ, and I'm going to instance child scene Abe. And then I'm going to hide these for now. But the VRM remapper is going to get all of our skeletons, all skeletons. It's going to be our array for child self.getChildren. And I'm going to pull the skeleton out of Abe, which sounds very threatening. Our skeleton equals child dot... I believe they're all named skeleton. Get node skeleton. Let me open this up. I'm going to rename it to skeleton. 99% of data science is munging data, and that's something that kind of bothers me at times. So that's Abe, who is now renamed to skeleton, and then AJ. Oh, rename this to skeleton. And get node skeleton. All skeletons. Sorry, skeleton not equal to null. I'm just gonna say if it is null, then I don't remember. Yeah, GDScript does not use is null, right? No, it can't. Print child name. Missing skeleton. X has no bones. Oh no. And then continue. Otherwise, all skeletons append. Does GDScript use? Yeah, it uses append. Skeleton. Cool. And then I want the skeleton info. I believe it was here that I said that I wanted to return the mapping from the index to like the properties. Sorry, right here. A bone ID to a feature array. I think I might actually want to return the bone name to the feature array. Because that means that we can have like the big list of I want to have sames and difference. So I can throw in like any two pairs of items and then say that these are the same, but these are different, these are the same, these are different. Yeah, I'm going to come back to this, like, because return a mapping from bone name to a feature array. It doesn't really change that much. It's just instead skeleton dot get bone name, and then I think it's bone ID. Yeah. So it's an important distinction. I would like to say I'll highlight this bone name to a feature array. And this is bone ID. Yeah, good. Okay, and now we're going to have the big pile O skeleton info. VRM, hold on. So how do we summarize skeleton by skeleton? I was using the VRM bone listing, so we have a ground truth. I was kind of under the assumption that there wasn't really a ground truth. So if we've got, if we have a ground truth skeleton, that is our OR skeleton. As long as that skeleton is basically the same. Sorry, for the viewers that aren't watching chat and for future me, the statement was, so I was using the VRM bone listing, so we have a ground truth. Yeah, this is... Terminology madness is always such a thing. Ivire and I were earlier, like I was misusing the phrase rig as meaning just like the skeleton. So like this is rig in my mind, but that's like that's not what that word means. That's totally my fault. And similarly, we have like a target skeleton in this case, meaning like this is our target skeleton. As long as we have one consistent thing that we're trying to hit, then we have an output. Like that is our target skeleton. Option 1 and option 2 will both work still for this. Since we're already so far in option 2, then it seems like not the worst thing in the world. Like you can get to option 1 from option 2. You can't go the other way around necessarily. Like you can. There's sort of a hack for it, but statement is VRM standard says hips mean AS hips and BB hips is both hips. Interesting. Oh, sorry, my eyes are so dead. I need to update to bump the font size on my laptop, but let me, before I get too distracted and lost in the nuance, I'm going to make this work for the two cases. So we've got the pile of skeletons. What I'd like to do is for each matching pair of bones, or for each unique bone, we've got all skeletons. In fact, we don't need to retain all the skeletons. Let's just say var bone descriptors. So bone descriptors is going to be a name to a list of features. No, to a list of features. So if we have, say, ring finger, that will map to the list of all the different bones we've seen that are also ring fingers. And then we'll know that if we just grab two things that are ring fingers, they should have properties that are like similar. So var skeleton properties, T's equals make features for skeleton. And then we'll give it the skeleton. Cool. And now we take all the different, so now we have this mapping for the name and features for all the bones in the skeleton, and we can build up this set. Or ranked highlight probabilities. Question coming in. We can say ultimate ID 0 means bone 1 on skeleton 1, bone 3 on skeleton 1. That's correct. Yeah. When we actually want to produce like a mapping, we'll just say like, let me jump over to main. We would say dt.predict, and then have the bone features A, bone features B, expanding these out, and then this will give us a number that's either 1 or 0, or close to 1 or 0. And from there, we'll say like, okay, all the pairs are matching up for a certain amount. I'm going to highlight or pull out a confusion matrix. Confusion matrix. If we look at this, I want a nicely colored one, ideally. So we'll get a chart kind of like this. And if you can imagine, this is like the left side will have like head bone, and this side will be like tail bone 1, ring finger, index finger. If the match between head and ring finger should be very small, and the match between head and like skull should be very high. So we'll get this very nice Technicolor heat map, basically, of how much each bone in our left skeleton matches to each bone in our target skeleton. And then we just have to take a path that for each row in our target skeleton, we pick the best match that isn't already used in the source skeleton. So you can imagine, as long as we pick one unique element in each row and column, then we get no duplicates, we get no double assignments, and we also know basically how good our match is, which is kind of a handy feature to have. So jumping back, it'll be something like this operation here. The interesting part is doing all this in Godot instead of like actually having unit tests, because I'm sure I made some kind of mistake. Before I forget, PRM requires basis identity for rotation. What happens if a bad match and occupies a slot? So it's possible. Like if we say, let me pull up that example again. If we are 100% confident that a head matches to a hip bone because somebody's head is in their butt, then we will lose out on we'll get two swaps, if you know what I mean. We get the head matching improperly with the hip, and then the rest of it basically proceeds as normal. The hip will also mismatch because we don't have a bone assignment for the hip. We'll have it instead like the head is taking up that space. So if we're careful about how we select things, like you'll notice in this column, like I believe these should total to 1. something like that. 0375.5. Yeah. We can pick values that trace out a path which maximizes the probability that something is true. If we do have a really ambiguous, like if there's one bad match, but all the others are really good matches, it's still possible that we'll end up with a case that is still workable. It's not a guarantee, but it's a possibility. So that kind of second degree of checking tends to help us out. If we do have a case where we just like spectacularly misclassify a head, that's something that we want to look at. In fact, one of the nice parts about that is if you manually override parts of that decision matrix, like if you say like, no, this one definitely matches with this one, probability of 1.0, doing that fix and then retracing the path will actually fix the rest of the bones too, which is kind of nice. Okay, so we now have skeleton properties for this skeleton, and now we want to go through each of the bones for var, too much time in Python. For name in, I don't think we can do iter items. Skeleton properties. We cannot do that in Godot. I'm just going to double check. I don't think we can. Dictionary. The for each mapping for, do we have items? We have keys and values, but not iter items. Okay, so we just got to do this. That's okay. In skeleton.keys. If name, if name not in bone descriptors, and I forgot GDScript does not have descriptors.has name. If not, then bone descriptors name is equal to some dictionary. Some list. Can we do this literal? Nope. Okay. Otherwise, we're going to just append this. Bone descriptor descriptors name append skeleton properties name. There we go. Now our bone descriptors will have this for each pair. We'll have a pile of matching features. We can now sort of exponentially blow this out by producing the pairs here, or yeah, I think let's produce all the pairs here. Build all possible pairs of bones. I'm going to do that right now. So we'll start by producing the pairs which are positives, and then we'll produce the pairs which are negatives. And this will be a bit of an exhaustive list eventually, but for just two skeletons, I think it's going to be okay. It'll exponentially, combinatorically explode, but in a way that we kind of want. So for bone name A in bone descriptors dot keys, for bone name B in bone descriptors keys, we'll produce the bar feature vector. Vector is going to be equal to a list, and then feature vector dot extend append array, and then bone descriptors bone name A. Sorry, I need to iterate over bone descriptors for this. This is going to be an array of arrays. So for bone array A in bone descriptors bone name A, and then for bone array B in bone descriptors bone name B. You can see that once we get into for loops, it gets crazy. We want to extend the feature vector with bone array A, feature vector append array bone array B, and then label equals so bone name A equals bone name B. So this gives us label is going to be true or false. And now we just have to take our feature vector and array and make our training data, which will also be an array. It's going to be an array of tuples, which I think I can use inside of main. Features and then the labels. Okay. So features, we'll have to worry about the ordering. That's fine. Where was I? Features. It's going to be examples, labels, and then examples.append feature vector, and then labels.append bone name A is bone name B. Because if they have the same name, then we're going to assume that they're the same bone. Cool. So we've got our labels, we've got our examples. Now let's train our model. We should shuffle this. It's not as important. Oh, hang on. I missed a bunch of comments. Sorry. We can explode it with more animations. Some issues with T-pose. Request a CSV from this too. Yes. I can definitely make a CSV of this train data. In fact, that would be a really good thing for me to check out so that I can run it like elsewhere. And it would be good for us to debug. I'll do, what is it, CSV, right? CSV. Store CSV line. Okay. I'll just copy paste. This feels really lazy, and I apologize, but that's what I want. Debug, save the CSV of this data. So this CSV is going to have, I think, will it have a bunch of columns? Well, open user file dat file write. Can I store? These are all going to be floats. So f.seek. All right. I should be at the start. Why is this complaining? Oh, because I indentation. And again. Cool. Sorry, I didn't mean to drink that loudly. All right. F.store float. Store float. I need to write all of the labels and then all of the values. And then the value. I don't think that GDScript has a zip, is it? No. That's all right. So for ID in range 0 to len examples. I should probably just actually do this while I'm iterating over all of them. Yeah, I'm gonna, like, just in case we crash because we're out of memory or something like that, I want to store. I shouldn't have to. This should be fine. It should be okay, but debug save CSV for I in range, I in feature vector. F.store float with CSV line. Values is pool string array. This is not going to be a pool string array. This is going to be, do you prefer tab TSV or oops, just looking at the chat history. There's a built-in write CSV in Godot if you prefer tab TSV. I don't have a strong feeling for tab versus comma, like it's all the same to me. The thing that I do think is going to cause problems is instead of being a pool string array, this is a pool float array. I mean, I can try it anyways, and maybe it'll be fine. But, oh, sorry, I just remembered something about append array. Let me really quickly check array, because I don't remember if this returns a new one at the end. Okay, so this does this modifies in place. I've been struck by that in the foot, and it does not feel good. All right, I think I can actually just. I don't want to add it to this feature vector. And I don't want, like, if I add it to the feature vector, it becomes a data leak. A data leak can happen in data science if you happen to append a feature that is extremely predictive inside your training data. Like, at one point I trained on a model where I was doing some work with natural language processing in the patent space. And we wanted to see which patents were very likely to be used in litigation by patent trolls. Yeah, it's test cheating, as iFire says. That's exactly what it is. We found a model was performing very well, like suspiciously well, like 100% well. And it turns out that one of the fields I was going into the input was whether or not things were used in litigation. So go figure. Make sure that whenever you're predicting something, it doesn't end up learning. The answers are not stored inside of the test questions. As satisfying as it is when you're a kid and you're like, oh, the next question has the answer to the previous question. All right. But I'm going to come back to the CSV storage. I'll figure it out offline, and then I'll send it for a CSV. Also, I'm going to throw all of this on GitHub. I do that most of the time anyway, so it'll be there, and it should be quicker to modify. Train our model. So we want our var rf is going to be, sorry, dt is our decision tree, decision tree dot new. And I don't remember if so we have predict, sample, predict with probability, save to JSON, load from JSON, train. It's samples as an array and labels as an array. And I'm not going to cap the depth of the purity now. So t.train, and this will be examples and labels. I think that's it. So the first thing that we do, train examples labels. Examples labels. All right, let's spell it right. LABEL versus LABLE has been a point of great pain. Because again, like half of the people that I work with are from Great Britain. So when it comes to naming things like variables, labeling the number of L's in that, or coloring, it's a fun problem. Okay, and now, start debug stuff. When we do a ready, we're going to perform also a VRM remapper.train. This is lazy, but deep breath, here we go. Print training model, print trained. And then, inside of train, we should also save our results. So dt.save to JSON, print. And there it goes. Chugging away. It's possible that it looks like my machine's keeping up. Over 3B. This problem. Yeah, it's the trouble is I don't always understand the American spelling of things either, which is weird. All right, so this is coming from the pairwise permutations, and it looks like, oh no, Stack Overflow. I think it's perhaps because I didn't cap the depth on function train, and it is okay. So we've got two labels which are possibly different, but what we can do to work around this is to cap our depth. Max feature depth. I just need to remember what the name is. Train max underscore depth equals 15 is actually probably way more than enough. Oh, right, you can't do named arguments in GDScript. Oh, that is a huge pet peeve of mine. I need my named arguments. It helps me so much. By the number, cap it by the number of bones. I don't think it's a... Okay, there we go. Looks like we got... Yes. So we have our tree that is output. I don't know what all these backslashes for. Oh, this is because we're recursively configuring the trees. Oops. So the save to JSON, I believe, is encoding the child nodes also as JSON, as dict. Save to, yeah, this is the stupid problem. That's fine. Func, I think as dictionary. And then we can just do take this self.as return this self dictionary left, self dictionary right, self dictionary self left dot and then here I should just do as dictionary is this if self dot left is not null, then self dot left self dictionary left is equal to left dot as dictionary, and if self dot right is not null, then self right dot as dictionary, and then this is okay to remove and I need to return self dictionary. So we save the JSON, self dictionary, this is fine. And then JSON print self dictionary. Then when we load from, parse, load from JSON, I think JSON parse self dictionary, I think there's going to be some issue with the script new. The load from JSON parsed. I think we can just do load underscore from JSON can just be equal to this. I think. Yeah, I'm gonna comment this out and then just do self.left equals parsed left. Same thing here. I know that Godot has a nice way to save scenes now, and I really should use that, but the advantage here is you can actually open it up and debug it and see what's going on. Only save to JSON at the end, keep it as a dict. Oh, yep, I'm half a step ahead of you in this case. So we're saving to JSON at the very end. We're using this new method as dictionary, and then handling it like that. So let's see if that gives us our training data, or gives us some pretty print. Training, cool. And I think it's a little truncated, but we can just write this to a file. Label confidence, probably false. Feature 7, threshold 5, impurity index. This looks actually pretty okay with just the small 2 samples. Like, it's definitely not perfect, but let me see if I can do like a predict. So we've got our, I'm also going to return the trained model, so print that and then return DT. Excuse me. Hiccup. Excuse me. And then we can pairwise iterate over both of these and say, or pairwise iterate over the two models to map them together. And yeah, eventually we'll just be doing something very similar to basically to this, except we'll have the skeleton on the left and the skeleton on the right, and we'll be doing dt.predict with probability, and then this will be the left bone feature and the right bone feature concatenated together. And that'll be it. So those are the big details. I'm going to take some more time to evaluate this. Like, I need my test set of stuff. So I've got AJ and Abe right now, and there are 23 more that have to get put together. But I'm going to upload all this to GitHub, and then I'll share it with everybody, and I'll post whatever trained model is finished so that we can just like straight copy paste it into the decision tree. I think the only files that people will need after this is all said and done is the make features for skeleton method, the compute bone, and then decision tree. And then if you just paste all these into one file, it'll map things together. And that should be it. Okay. It's been an hour and a half. Maybe we'll help you set up the skeletons. I appreciate the offer very much. It could be cathartic. I'm going to hack a little bit. Let me know what the layout is. Actually, since I've got like 20 minutes left before I have to do anything, I'm just going to go over what the actual process I use is. So I do file import, and then I do BVH, and I've got Abe, AJ, Big Vegas import. I'm going to get rid of AJ. Big Vegas. I'm going to go into pose mode, select everything. What's going on here? Oh, just standing up. Okay. And I'm going to shuffle these over by one so that I can keep the existing animation, take everything, reset the pose, and then insert a keyframe for location, rotation, scale. And I'm going to take a quick look at the hips, pelvis, spine, facial, and M joint. That's okay. And I'm going to do object mode, file, export, FBX into Big Vegas. Bake animation, leave everything else, export. And now there's a bit of a song and dance around cleaning it up once it's in here. So Big Vegas, open anyway. I'm going to take Big Vegas, drag them up to the root, rename, get rid of this root node. I think this transform is, yeah, set the scale back down to 1, rename to skeleton, and then these nodes are named differently, but as long as the bones themselves match up, then we're okay. So bones, this is a problem. See, New Vegas right is right, whatever, New Vegas right, hand, thumb 3. If the bones aren't matching between two skeletons, then we'll be throwing bad data into our setup. So I'm going to say skeleton with bad names. And the reason I'm renaming this from skeleton to, hang on, I'm running Blender 3.2. Yeah. I'm still going to save this already as Big Vegas. Yeah, I think it's just a matter of like renaming these to hips and spine and pelvis and all that jazz, and then it should be okay. But I deleted the other skeletons. That's okay. But this is the approach that I've been using so far. It reset it, and then as long as we append them to the VRM remapper with the appropriate bones, then it's okay. The skeletons for AJ and Abe are very different, and I think Vegas also has very different skeletal structure. Yeah, there's this, whatever that is. Pointy boy. Okay, well, I'm going to keep going through this. The next thing that I want to do is make an evaluation. So I'll probably import 5 or 6 more, and then I'm just going to see exactly how well this works out between a golden validation set and the ones that we've got so far. I will officially, sorry, not officially. I started reading something there and my brain got crossed over. I'm going to upload this to GitHub in short order if it's not already there, and then I'll send out the notice, and the recordings should be stored in the VOD channel on Twitch if people want to go back through it. So with all that said, thanks everybody. It's been a pleasure, and I will be back online sometime in the near future. Take care of yourselves.